Alrighty. Hello and welcome, everyone, to Engineering the Future of Kubernetes for AI at Scale. Today, we're going to be talking about how Google is working with the open source community to drive industry-wide standardization and transformation. I'm Kaslin Fields, and I run GKE Developer Relations Engineering here at Google Cloud, where I focus, of course, on Google Kubernetes Engine, as well as open source Kubernetes, where I'm also a maintainer as a co-chair of the Special Interest Group for Contributor Experience. And I have with me on stage...
Hi, I'm Jago Macleod. I'm an engineering director on the GKE team, and I lead Kubernetes at Google and various other parts of GKE, especially in the upgrade side and a bunch of agentic work we're doing now.
And I'm Boaz. Rant. I lead DevOps for Palo Alto Networks.
And if you want to hang out, you're welcome to. But if you want to sit down, you're also welcome to do that. They'll have sections a little later in our presentation. So this is our agenda. We're going to talk a little bit about what we mean by driving transformation through open source. Then we're going to talk about AI apps and agents, compute for inference, and networking for inference. I'll explain a little bit more about what I mean by that at the end of this first section. So let's talk about driving transformation through open source, why open source is so important for standardizing patterns and realizing the value that AI can bring to your businesses. Who here has heard the classic line that Kubernetes treats your apps like cattle, not pets? Fewer than I thought. I am old. So if you've heard this line before, it's meant to talk about one of the earliest and still very true today value propositions of Kubernetes, which is that it abstracts away the underlying hardware so that you can focus on the applications that matter to your business. This is great in a world where we have a lot of stateless applications that run on CPUs and don't have too complex of memory and state requirements, where something needs to make sure that it has the same IP address all the time, for example. Kubernetes auto-healing capabilities often traditionally have meant that the workloads will restart, and so they might not always be there. So when something ephemeral and stateless works, the cattle versus pets analogy works really well. But we quickly realized in Kubernetes that a lot of people want to run workloads that do need a persistent identity or access to storage. And so the community started to make changes to Kubernetes to enable users to run stateful workloads. We introduced the concept of pet sets in 2016, which we quickly renamed to stateful sets. Any stateful sets users? You wish that they were called pet sets? It is funny. So this was a new type of deployment that could be used to run stateful workloads like databases, where the application needed a persistent identity and access to storage. Who runs databases on Kubernetes today? This is a lot of questions, but I knew there would be some. It works. You can do it. Now, in a world where we've seen a massive shift toward AI workloads across the industry, there are new requirements that Kubernetes needs to meet. That story of Kubernetes abstracts away the hardware, so you don't have to think about it, doesn't work so great when a lot of your users want to run super high performance, super hardware-sensitive workloads, where they want to know that their workload is running on the latest GPUs or exactly which type of hardware accelerator it's running on. So this moves us from a world where the type of underlying hardware doesn't really matter to one where it really, really does. Plus, those workloads need data, and lots of it, and fast. Sure, we introduced stateful sets 10 years ago, but the challenge of high-performance data access and management in a distributed system continues. So today, we're going to highlight what we're doing in Kubernetes to address the challenges of today's AI workloads. Some of you may be sitting here thinking, is there really such a massive shift toward AI workloads that it warrants all of this? Welcome to Google Cloud Next. I hope you're having a good time. You're not just going to see it here at Next. Of course, hopefully, I imagine you've seen it everywhere here. But KubeCon was a month ago in Amsterdam, and if you were there, you saw it there too. Earlier this year, the CNCF released their report from their annual Cloud Native survey, and one of their findings was that 66% of organizations running Kubernetes were using Kubernetes to host generative AI workloads. So yes, especially as the open source community trying to serve these users, we really need to make sure that we work well for these types of workloads. And let's define this problem space a little bit more. When we talk about AI workloads, what do we mean? Google Cloud has a definition in our documentation. This is one of the statements on that page. As I mentioned on the cute cattle and pets slide, AI workloads are data intensive, and they demand specialized parallel processing hardware like GPUs or TPUs. Just say it. There's two types of workloads that we're going to consider in this presentation. One is inference. Inference, or serving, refers to running an AI model on hardware so that it can be used by other programs. A model is just math. It is not a program. It is not code that you can run on a computer by itself. You need to do a little bit to make sure that the computers can run the math that is the model. So we'll talk about model servers and how you do that. The other is AI apps and agents. So these are programs, actual code, that runs on computers that takes a dependency on models. They're programs that use non-determinism that's offered by AI models to achieve some goal. And as far as we're concerned in Kubernetes land, they're basically just microservices. Most of the stuff we already have in Kubernetes works really well for running AI agents and applications, though there are a few things that we do need to consider, and we'll go over some of the new features specifically designed for these workloads. So we're going to break this down into 3 parts. Number 1, we're going to talk about those AI applications and agents. Like we said, they're mostly just microservices, but we'll tell you about some of the unique things that you have to consider. In part 2, we're going to talk about compute for inference, the problem where our users now really care about that underlying hardware and want more granular control over it. I'll show you what we're doing there. Well, actually, Jago will. And then, in the last part, we'll talk about networking for inference. You've got these big specialized workloads that need to run across many pieces of hardware. The networking between those pieces of hardware has to be top-notch to achieve the highest possible performance, which is really important if you're trying to get an AI product to market in the speed that our market is operating in right now. So let's start out by talking about agents. Everybody's running agents, and if you're not, you might want to think about it. So what is an agent? We talked about how an AI application or agent is a program that takes a dependency on a model. In the developer keynote here at Google Cloud Next last year, we announced Agent Development Kit, or ADK. That's our framework for building agents. And in the demo, in the keynote, the presenter, Fran Hinkelman, who is also in DevRel at Google Cloud, described agents this way. And I think about this statement a lot. I think it's a really useful framework for understanding what an agent is. She said, all you need to build an agent is instructions, tools, and a model. Today, we would probably also add skills to that list, but in my opinion, it doesn't change the list of components. So by instructions, we just mean natural language instructions. For example, when you talk with an AI and ask it why the sky is blue, why is the sky blue would be your instruction. Skills, I would argue, are part of the instructions. They're just natural language descriptions of how to do a thing, usually in Markdown format. They give the AI more context about what it needs to do and how to do it. Skills are really cool and useful in that they can make the work of getting the AI to do the thing a lot easier. But they're basically just additional natural language instructions. Then there's tools. So look, non-determinism isn't the solution for everything. Sometimes you want something done in the same way every time, and deterministic code is great for that. Say, for example, if you made a really cool Python function that makes a great visualization of your podcast listeners based on your typical podcast listener data format, and you don't want the AI to make a different version of that visualization every time you ask it to. You could use a tool for that, like I did. And so tools can help you get more reliable results from your AI applications and agents. They can help you avoid, but not prevent, hallucination problems. So these, as you can imagine, are hugely valuable and powerful. Tools make agents so much more useful and reliable, in my opinion. And then there's the magical non-determinism, math, or a model. So a model is just math. Math that does things that you can't anticipate. It's non-deterministic. You give it a problem, and it figures it out, possibly by realizing that it needs to use some tools. We'll talk more about models and how to run them later, but this is basically what we mean by an agent, an application that takes a dependency on a model. And according to that CNCF survey again, 52% of organizations don't build or train their own models. For example, if you're using Gemini, you're going to use it through a model as a service. If this is you and you don't care about running your own model, how can Kubernetes help you? A big new feature or project here is Agent Sandbox. As AI agents become more autonomous, they increasingly need to write and execute code or do things with computers. You ideally want to create agents that are doing something meaningful for your business, and that introduces some risk. The Agent Sandbox provides a vendor-agnostic custom resource definition and controller, obviously, because that's part of the custom resource definition, to securely isolate model-dependent workloads. So what does it provide? To ensure above-average isolation, sandboxes use runtimes like gvisor or Kata containers. There's some choice in the configuration here. And to provide deep kernel and network isolation between the sandbox and the host, we use something, we typically use gvisor when we deploy it ourselves. And you know what else is still a problem for everybody? Cold starts. The Agent Sandbox definition in open source also provides a standard concept of warm pools, which ensures that a specified number of pre-warmed, fully initialized pods are always running and ready to be claimed. So that means that you can spin up an agent in a sandbox, or even swarms of agents in sandboxes, in under a second. Let's see a demo. So who's seen the ADK web UI? Who hates it? Sorry about that. I didn't make it, but still sorry about it. So this is the ADK web UI. When you create an agent with Agent Development Kit, it's a framework that basically you specify which model you're using, what the instruction is you want to give it, and what tools it has access to. And boom, you've got an agent. And in order to test that agent, you've got some kind of system instruction that's specifying how that agent should behave and things like that. So you want to be able to test it by sending it prompts. So this is a convenient interface for doing that. And what I have running here is a simple like Python coding agent. So I'm going to ask it, write a Python script that says, hello from the isolated sandbox. And what it's going to do is it's going to use a tool that it has access to run this newly generated, untrusted code in an agent sandbox, running it in an isolated environment. You can see here, nice thing about the ADK web UI is if you click the lightning bolt one, you can see the code that it generated, which is right here. So it said, print hello from the isolated sandbox. Good job, model. And then there's a check mark one here, which sometimes I have to click away from and then back into. And this has a result. So this is where it ran the code in a sandbox, and it gave me a result. And then it gave me a natural language description of the result, which is exactly what I expected, hello from the isolated sandbox. And I'm going to hop over here. So what I have going here is kubectl get sandbox claims in my namespace, and I have a watch on it. So I'm looking for sandbox claim objects in my cluster. This is the object that the custom resource definition allows you to define in your cluster. You first define a sandbox claim template that says, if I had a sandbox, I would want it to look like this. And then when you need one, it makes a sandbox claim that adheres to that template. So you can see here I've got a couple of them. This is actually the live demo that's running on the show floor. If you want a deeper dive into this, we have it running on the show floor. So there's one from the show floor, and there's one from me. You can see that the characters here are different. That indicates that they're separate sandboxes, even though it has multiple instances of them. So that's cool. I showed you that you can make sandboxes. But what's really cool about that? So here's a demo that one of the engineers working on Agent Sandbox created. It's called Barkland. And the agents in this are dogs. And so you can specify a number of agents that you want to spin up. We're going to try spinning up 200 of them. And when I start the simulation here, those warm pools I talked about, We're spinning up 200 agents right now. We're at 150 already. Sometimes it pauses for a little bit before it finishes up. But you can see that the warm pools are really powerful in enabling you to spin up a lot of agents really fast. So that's pretty much what I've got for you in terms of demo today. If you want to dive deeper into Agent Sandbox, stop by the show floor. We would love to show you more. And another feature that I want to talk about here is the GKE pod snapshots. So this is a GKE-specific feature, and it allows you to save and restore the exact state of a running pod. This can be great for spinning up a whole bunch of copies of the same snapshotted pod really fast. The most common use case that I get when I talk with PMs or engineers who are working on this about it is models, actually, which this is not in the model section. But when you need to spin up a model, you need to get the weights for that model in order to run it. And so if you have a snapshot that already has those weights in it, you can spin up additional copies of that model server really, really fast. So this can be really powerful for that. Another really cool use case here is for long-running agents or long-running batch workloads. Honestly, I see it more for the batch workloads thing. But if you have a really long-running workload on your cluster, and it's using up your GPUs, let's say, and you need those GPUs for something else real quick, snapshot the running workload, take it down, use the GPU for that other thing, spin them back up. A lot of really interesting opportunities here with pod snapshotting. Next, we've got in-place pod resize. Everybody loves in-place pod resize. So this is GA in Kubernetes 1.35, so open source Kubernetes feature. And it enables you to dynamically modify the resources assigned to a container in a pod without restarting it. Non-disruptive resize. Obviously, the biggest benefit here is minimizing downtime. You could already resize pods, but having to do it manually was clunky, and doing it automatically was disruptive. If you take out the disruption, you've got a whole new world of opportunity in terms of uptime and in terms of resource efficiency. Not only can you potentially bin pack more efficiently and autonomously over time without impacting downtime, but also if you have workloads that need a burst of resources at the start and then they need less when they're up and running, there are lots of great opportunities here that you can make use of with in-place pod resize. I also want to mention here, horizontal pod autoscaling is very well known, where you create more copies of a pod, of a workload, so that you have more to load balance against. Vertical pod autoscaling is where you resize the requests and limits on the pod. It used to be that if you use vertical pod autoscaler in auto mode, it would kill your pods when it needed to resize them. And if you did it in manual mode, it would tell you what to do, but it wouldn't do it for you because it would be disruptive if it did. This opens up such great opportunities where you can non-disruptively change the resources available to a pod. So this is what we reviewed in the AI apps and agents section. These are all features that can really benefit a wide variety of types of applications on Kubernetes. Agent Sandbox for isolating agentic workloads, GKE pod snapshots for snapshotting and restoring running pods, and in-place pod resize for non-disruptive workload resizing. And next, we're going to hear from Boaz about what this stuff means to him.
All right. Thanks, Kaslin. Very good, cool features coming up. So I want to cover a feature that is useful also outside of the AI context. We in Palo Alto Networks manage a whole lot of clusters, many thousands of them, in fact. Actually, me and Jago kind of was trying to figure out what's the number. So while managing thousands of GK clusters, very fun, bin packing in thousands of clusters, even more fun. IPPR, the best thing in Kubernetes since sliced pot. All right. We have been waiting a long time for this one to hit GA for GKE. The only logical thing to do is, you haven't seen this feature before, is to take your favorite path pod and randomly change the requests and limits and see how it goes up and down very quickly. All it takes for this to work is to add the sub-resource equals resize if you're running it by kubectl. This is over here. And you can see I just randomly played with a pod, 0 restarts, just changing the requests. And this is, for me, it's pure magic. Consider millions of pods. Every small change makes a difference. The real-life example we've been seeing a lot in the applications is applications with intensive starts. Ones with Python and heavy imports as one example. Init containers just do not fix this use case. For example, a pod requiring a half core to start, but idles at 0.02 cores. As hopefully you can see on the left arrow, the pod is born, taking half a core for a good while, forcing us to use high requests and limits to accommodate this pod. On the right arrow, we use IPPR, and we let the idle live. And the cluster now has the potential for perfect bin packing, and all the savings can go to Gemini tokens. With first order of business, when you hit this, after you play around with this feature, it kind of forces you to create an operator to automate this across the many pods. But there's definitely a lot of great potential in this feature. That's it. That's it for me. Jago? Thank you.
Thank you. I think one key message from that is, even if you're sick of hearing about AI, that there is an unprecedented amount of resources going into evolving our technology at every layer, and it benefits every single workload we run across every customer. So pick up on these things. Don't wait to be running models necessarily. But as I mentioned early on, I lead open source Kubernetes at Google. And a major investment, really the biggest pivot from the beginning of Kubernetes, has been evolving to meet the needs of what I call the next trillion core hours. The next wave of adoption is really in these, both the training, the inference, and then pulling it all together in reinforcement learning and agentic applications. And so we're going to go through a few innovations and what they mean and why we're doing what we're doing. So first off, this was also a gem in the CNCF's annual survey, which is that 47% of organizations deploy AI models occasionally, with only 7% deploying daily. Like this, I don't know, it was the only that caught my eye. I was like, 7% of organizations are deploying daily. That's amazing. I think that should be a different qualifier. But it means that it's exiting the prototype phase. The MIT study that talked about how much folks are failing with AI deployments. We're clearly moving past that phase and into real production use cases, and I talk to customers every day who are succeeding in this dimension. So first up, we're going to talk about DRA, or dynamic resource allocation. And the first order of business in Kubernetes and evolving for AI was becoming accelerator native. And this has been a key theme for about a couple of years now, shifting from cloud native, making cloud native accelerator native. And at the beginning, Kubernetes had two main resource-related numbers that we cared about. It was CPU and it was memory. You could have more or less of either of those, but essentially a node is a node is a node, and they were fungible and interchangeable, and it didn't really matter which one you were running on. Fast forward to now, and hardware is often specialized, it's often sparse, and sometimes very expensive, so you really care which one you're running on. So dynamic resource allocation is really about a framework for describing the topology and underlying capabilities of the hardware. So it might be an accelerator, it might be a network, and Kaslin will talk more about the networking side a bit later. But essentially, it's a way to describe in very rich detail the characteristics of the underlying hardware. So the workload then can express its requirements of the underlying hardware and get placed in a node or on hardware, on infrastructure that can serve its requirements best. And this allows you to improve the utilization across your reserved instances. And one thing I talk a lot about is how we're sort of returning to the data center world of a decade ago, where you have a fixed capacity and you try and fit the highest priority workloads into that capacity at a given time. With reserved capacity, and sometimes the capacity you want is not available in the region you're in, you end up in a box that you're trying to fill the utilization of reserved capacity over time. So it's a very similar pattern that we're seeing. The second project is LLMD. And LLMD is a layer on top of a model serving program that Kaslin mentioned earlier of VLLM, which is the software around a model. LLMD is a Kubernetes native framework or system for being on top of multiple nodes that stitch together a model that doesn't fit in one node. And so these multi-node use cases are challenging. You can route naively and take the same amount of time with every request, or together with LLMD and something called inference gateway or gateway API extension for inference, you can route to the correct node that has the information you're required. And so one key breakthrough in LLMD is this idea of disaggregated serving. And this is an industry trend you'll see more of. And it's essentially splitting two distinct aspects of serving or inference into different approaches. So there's the prefill, there's the take the context and the prompt that is describing the user's intent. And the second part is the decode, which is putting it all back together to return to the user. And it turns out that splitting these two into two separate approaches is an important optimization. And LLMD is pushing this forward. Another aspect is caching. If you don't have to go all the way to the underlying hardware, but you can maintain in cache, just like databases with caches, a similar pattern emerging in this space as well. And so this multi-node KV cache is a critical optimization aspect as well. And so as we move from the underlying hardware, there's still work to do, but the underlying technical challenge is essentially understood and well understood and moving forward in open source Kubernetes and available today in GKE is this DRA step. How do we describe the underlying topology of the hardware in its new form? And now we move to how does the scheduler make use of that richer information so that we can map a workload to the correct underlying infrastructure. And this is in progress right now. I invite you to show up to the SIG scheduling meetings and bring your use cases and your experience to help us shape this. But the form that it's taking is essentially learning from our work in projects like Q, with a K, of course, which you may have heard about, and alternative schedulers like Volcano, and pulling them into Kubernetes itself. So you're no longer succeeding in spite of Kubernetes, you're succeeding because of Kubernetes. And we go through this pattern fairly frequently, where Kubernetes doesn't have a core primitive, and it's super extensible and pluggable. So customers go and, or ecosystem vendors go and create an alternative scheduler or a plugin, and it becomes popular. And then it's no longer a differentiator because copycats show up. And so then we pull into the core of Kubernetes and bring those minds and people together to collaborate, and then innovation moves on to the next step. So it's a repeatable pattern, a conveyor belt. One of my colleagues calls it a conga line, which I think is kind of funny. But really, this is taking place in the workload API. And so some of the core features are scheduling multiple pods at the same time. And the value this brings is, without this, you schedule, 800 pods, and 600 make it onto the existing infrastructure, and 200 just can't be scheduled. So now it's waiting for the cluster autoscaler to provision a couple more nodes, and this takes time, and all of your capacity is just sitting there idle, waiting for these additional 200 pods to show up. With workload API and gang scheduling that comes from projects like Q, it will schedule that, or you can queue it up to be run when the capacity is available. So your infrastructure can do something else, a smaller job for a different team in the interim. And so this improves your overall utilization over time. The other is workload-aware preemption. So a low priority job is running, something more important comes along, you can kick out the low priority one and put it back at the top of the queue and do the one that is higher priority. And finally, this topology-aware scheduling. Especially in multi-node setups, it's NVIDIA compute domains or TPU pods. It really matters that workloads fit in, especially where the networking is going to be fast and performant and so on. So knowing more about the underlying topology helps the scheduler put workloads where they're most likely to run successfully. So we talked about DRA, LLMD, and then this workload-aware scheduling and topology-aware scheduling are two aspects of the same underlying effort. And these are sort of building blocks making up compute for inference. And as we talked about before, all of this investment becomes useful for every workload. So DRA is working for HPC workloads with our friends at SkedMD, now NVIDIA, that are working on Slurm to make Slurm run better on Kubernetes because it knows more about the underlying CPUs. And now we're going to talk about networking and using some of the same underlying primitives. I'm going to hand it back to Kaslin for that. Thank you.
Thank you, Jago. And as I said, if you want to heckle me on any of these, you are also still welcome. He knows all of these features very well. And one thing I want to call out before I dive completely into the networking is if you take away one feature from this talk, I kind of hope that it's dynamic resource allocation, or DRA, because it fundamentally changes the way that Kubernetes relates to your underlying hardware. It makes it much more able to manage your hardware much more granularly and makes it much more aware of the specific types of hardware that are running in your cluster. But let's talk about networking. The first one is DRA net, which is very similar to dynamic resource allocation. It's about managing the physical networking resources in your cluster more granularly. And it uses the exact same objects in Kubernetes that DRA uses: device classes, resource claims, and resource claim templates. So you can specify a type of networking interface that exists in your cluster and use it using resource claims and resource claim templates and device classes that your workloads can claim access to that networking resource. Because it enables you to manage the hardware network interface distribution somewhat separately from the hardware that it's actually sitting on, it can help you improve utilization of that hardware by making it easier to manage how you're using the networking hardware across your workloads rather than managing it per machine. Operations that require massive volumes of data to be shared and synchronized across multiple machines simultaneously are incredibly sensitive to network performance. So DRA net's ability to assign dedicated high-speed RDMA or TPU network paths can prevent network interference and dramatically improve data transfer speeds for your workloads. And I will mention, the PM had me put this in here. Managed DRA net on GKE improves bandwidth for distributed AI/ML workloads by up to 60%. And have you heard about the Gateway API? Who knows Gateway API? Those talks are packed at KubeCon. I think that's the most hands that I've seen of this whole thing. Good. Stop using ingress. So Gateway API is the new way that the Kubernetes community wants you to do ingress for your workloads. We had an ingress object in the Kubernetes cluster. The way that we thought people would use ingress is not actually exactly how people use it. So we kind of had to redesign how it works. And we created this API standard defined by the community of these are the things that our users need to manage ingress. But how you implement them depends on the actual physical networking of your environment. So we have the individual providers implement that API for their environments. So gateway API is really important. If you haven't switched from Ingress to gateway API yet, you should. We're not maintaining Ingress anymore. So GKE Inference Gateway is an implementation of gateway API. It's specifically a gateway class that moves AI-aware routing logic directly into the load balancer. When we talked about LLMD, we talked about context-aware routing. LLMD routes traffic based on an event-driven real-time index of exact KV blocks. If you remember, Jago mentioned the KV cache that map directly to the prompt or instructions that you've given to your model. So Inference Gateway relies on server metrics as well as prefix cache matches to help make sure that you're running your workloads on the right instances. So it does this at the load balancer level, while LLMD does it at the system level. So both of them can help make your workloads more performant, but one of them does it at the load balancer versus one of them does it at the system. LLMD has more stuff than that, but that's one way they're similar. We also released a blog post earlier this year about how Vertex AI, which isn't called that anymore, used GKE Inference Gateway to double its prefix cache hit rate, which makes it much more efficient in terms of hardware utilization and in terms of latency for its users. One of the main things that not Vertex does is provides models as a service. So it enables you to, it does the inference workload while your agents or your AI applications use those models. So Inference Gateway can give them huge performance improvements. So the QR code here will take you to that blog. A couple other stats from it. They reduced time to first token by 35% for the Qwen 3 coder model and 52% for DeepSeek. And they have graphs in the blog. They're great. So in this section, we talked about a few new features in Kubernetes that enable your AI workloads in terms of networking. So we talked about DRAnet, which uses the same objects in Kubernetes as DRA to allow you to granularly manage your networking interfaces and actual hardware, just like DRA allows you to do that for accelerators. And we talked about GKE Inference Gateway, which is an implementation of the Gateway API's gateway class that's specifically geared toward inference workloads. That's all I have for you today, and I'm going to review all of that. But also, you might be thinking, what about training? A lot of the features we talked about today are also relevant for training workloads, but we wanted to talk about them in a specific context, so we talked about them mainly about inference. If you want to talk about training, I'm probably going to head to my demo after this. Also, if you want to learn more about Agent Sandbox and the demo that I showed, follow me, and I'll take you there. But to review, we talked about AI applications and agents, which are instructions, tools, and a model. Agent Sandbox is a really useful project there, open source for isolation at scale. We also just released GKE Agent Sandbox, which is just the open source thing running on GKE. GKE pod snapshots, which enable you to snapshot a running workload, really great for startup and restore activities. In-place pod resize, which allows you to non-disruptively change the resources in a workload. Compute for inference, we talked about dynamic resource allocation. If you take away one thing, take away that, it completely changes the way that Kubernetes manages your underlying infrastructure and allows you to manage it more granularly. LLMD is a specialized framework for running LLMs across distributed infrastructure. If you've ever tried to take a monolithic program and run it across computers, you know that can be challenging. So LLMD can help make that easier with a variety of Helm charts, tools, and guides and examples for how you take an LLM and run it across hardware. Workload-aware scheduling is the concept of taking the scheduler in Kubernetes and making it a lot better at doing what it does for different types of workloads. Jago explains it way better than me. And then networking for inference, we talked about DRAnet, which is similar to DRA, but for networking, and Inference Gateway, which is, of course, Gateway API. And that's what I've got for you. If you want to try out that demo for yourself, there's a code lab. If you want to learn how to deploy Agent Sandbox on your GKE cluster, it also does DRA, LLMD, and Inference Gateway. Inference Gateway kind of part of as part of LLMD. So it can teach you to do 4 parts of the features that we talked about today.